function. So here's the last section before our test. It's all about the applications. Okay, let's just kind of, in general, you can read through the textbook for more of the details. In general, for exponential functions, they are useful when you want to model phenomena that either increase or decrease based upon the amount of whatever you're monitoring present at that time, based upon the amount of whatever you're modeling or monitoring at that instant of time. It's always based upon the present state. Now, one such thing we can do, if you look in the world of, say, finance, we can look at your compounded interest. How much is there? Now, if you look at it in this form, we'll say social sciences. We're looking at things such as population growth. So you can plan for a growth of a population. You can also look into health. And it's used to model the spread of a disease. We're going through that right now. That whole thing, when you look at how the COVID is kind of going up like that, turns to be an exponential growth rate that we're experiencing right now. And it's also in, say, archaeology. You can monitor the radioactive decay, so carbon dating comes into play here. Or even in health, how long a drug stays in your system, anything that decays. So this, model the decay of a substance, either in the environment or in our human bodies. This is all modeled using an exponential function. Okay, we'll look at a couple of types of models like that. And the other type is a logarithmic function. And what can this be used? Well, this is used to kind of create scales for either large or very small quantities. It's useful, one of its many properties, useful in creating workable scales. Usually they're dealing with very large or very small quantities. For example, in your swimming pool, you have your pH scale, the pH level in the water. This monitors the amount of hydrogen present, and it deals with the acidic or the basic nature of it. Models using very small numbers that are like 0.02, something like that, really small numbers. And instead of having to deal with small numbers, it rescales them in a way that we don't have to deal with that. Another application over here is with earthquakes. And we have something, we're going to look at the most basic, the first fundamental one that was created, the Richter scale. Although now there are others that deal with that. So the earthquake and the Richter scale to give you the magnitude of an earthquake. It's very useful for scales like that, really small or very large scales. We're talking about great motion of things, and you don't want to kind of scale that down in a way. And it's also used to a number of different other sort of things. It's in computer science, it's used to model what they call computational complexity of an algorithm. When you want to count how many, addition, subtraction, multiplication, division, whatever arithmetic operations you do, they use that to kind of scale one algorithm against another and compare them. And there are many others. There are several others that are there. So they're connected. They're inverse functions of each other. One function is the other function, argument. And the argument has to deal with these scales, and the other part, how it grows and decreases. Okay, so we have two different types of functions that model two different phenomena. We're mainly going to be using the scaling option, less of the model, but more of a scale. So that's what we'll look at for the logarithmic. Let's take a look at the exponential, and we'll look at two of these. The general idea is we have two types of exponential functions. We have increasing and decreasing exponential functions. So let's start with the exponential models. All of them come from one particular form. You might have your, I'll put it as an, f of t. We'll usually deal with time, of modeling over time, is equal to some initial value. We'll call that, say, f0 e to the k times t, where k is a constant. And depending on the type of model, that changes. Now, if k is less than 0, it's a negative quantity, then we're dealing with exponential decay. We're dealing with a decreasing exponential. If, on the other hand, k is positive, greater than 0, well, it's an increasing exponential. Because you could have, this is like e to the minus 2t, negative exponent, or e to the plus 2t. This is exponential that increases as t increases, and this is an exponential that decreases as t increases. One decays and one increases. Okay, so let's take a look at some of the standard approaches for this. And the first one I mentioned was radioactive decay and carbon dating and that sort of thing. So it was discovered back in the 1940s that, the amount of carbon in a living thing stops growing as soon as the living thing dies. And then it starts to decay at a fixed rate. And it was very useful because then you could date certain things in our history. Like if you cut a tree down and made paper out of it, you can look at the amount of carbon in that paper over the years, carbon-14 in particular, and it decays at a fixed rate. Although, since we've been kind of polluting our environment with a lot of other carbon things, it's not as accurate as it can be, so they have to make some adjustments based upon what we put back into the environment. But if there was no extra carbon put in, you can just watch it decrease. So there's just a few caveats in terms of how precise it still is, but it's reasonably precise to get a general age. So let's take a look at the first thing, which is carbon dating. And this is going to be the idea that carbon in a living thing kind of decays because it's no longer alive to create new carbon, new life-forming carbon. It just decays away. So this is all about the radioactive decay. And it's always based upon some amount. So we're going to let the function be a of t, where a represents the amount. And then a0 is the initial amount. That's the initial amount present. And here's my exponential. In this case, it was chosen. You could use 2 to something, but we use the natural exponential function. This is used quite frequently. In computer science, it might be 2 to the t. But here we have some, like it's a minus kt. It's a decreasing in this case. So in this case, we put the negative with it, and we're just now going to get the positive value of k over here. So we're going to assume that it's a decaying exponential. So I put this sign, this k and that k is the negative of this k. So I just want to explicitly show that's a decreasing. Now, one of the key things, anytime something decays, be it radioactive or if it's absorbed in your body, there's something called the half-life. A half-life. And that's the time for the initial amount to go down to half of its initial amount. This is the time it takes for the substance, whatever you're monitoring, to decrease to half of its amount. And that varies from, subject to subject, from, radioisotope or quantity to quantity. That is usually given. This is usually a given phenomenon. That's given. That's the given value. Because you scientists study things and they can measure it, monitor it over the years, and they say, okay, we know what it was, leave it alone for a while, remeasure it, and then you can see where it's going and extrapolate and get its half-life. So that's always given. Now, how is it related to this over here? Well, let's take a look at that. So let's take a look at this half-life process. Meaning, I start out with A0, an amount A0, and I get to half of that A0. So that's what happens. There's some time, the half-life time, when my A0 over here becomes 1/2 A0 equal to my initial A0, e to the minus k, and t sub h, time of the half-life. So I've given some half-life time. I don't know what it is. I'm doing it in general. And now I'd like to find out what is k. How does k function over here? Okay, so what do? Well, I can solve this equation. I can divide both sides by A0, and it's independent of the initial amount present. So now I'm looking at this equation. 1/2 is equal to e to the minus k and my time for my half-life. How do I solve this? Well, I can take the natural log of both sides. We learned how to do, in the previous section, solving exponential equations. So this gives me the natural log of 1/2 is equal to, this cancels out, it just gives me a minus k times my time for my half-life. Okay, so I'm working with this a little bit. Let's continue a little bit further, and we'll get our model that we can use to model any phenomena that decreases based upon a half-life, but we can separate it out. Now, sometimes you often rewrite this. I can often take and rewrite this as the natural log of 2 to the negative 1 power. That's equivalent to 1/2. I can bring that my negative 1, so that is equivalent to minus the natural log of 2. So the left-hand side I can actually replace with the negative of the natural log of 2 is equal to the negative of k times the half-life time. The negatives cancel out. Solving this for k and flipping around, I get k is the natural log of 2 over the half-life time. So if I'm looking to model how something decreases over time, this is a general model that I might choose. My amount present as a function of time is equal to some initial amount that was there, and then e to the minus, and then I put my k over here, which is the natural log of 2 over, I'm just going to put it as half-life times t. Now that's my variable. That half-life time is a constant. That depends upon whatever it is that you're monitoring. Now if I choose to model carbon 14, so the half-life of carbon 14 is equal to 5,730 years, approximately. You know, it's a rough approximation. And that's its half-life. So let's use that to model something, see if we can, what information we can find out about a particular phenomenon. So here's an example that's in the textbook. So here's an example of how we might use it. So you're at an archaeological site, and you find an artifact, archaeological artifact. Was discovered and was determined the current amount of carbon 14 present, was discovered. And it was they put it through a test and checked out the amount, because they know living things have the same proportion of carbon in them, so they keep that. And it was discovered that the original amount is 10%, that the amount of carbon 14 present is only 10% of the original amount. They can then use that. The question they would ask is, how old is the artifact? Gives you a sense for how old that particular site is. When did that civilization live? And that's how they do it. Very simple approach like this. I mean, obviously measuring the amount is sophisticated. That's a sophisticated scientific experiment to do. But then once you get it, you can just plug everything in. Okay, let's see, how do we do this? So what we're going to do, this is our model. And I start out with some A0, initial amount. And now I'm down to, 10% of that A0. Well, what is that? Well, that's 0.1. I've got my percentage as a decimal times A0. So what I'm doing is I'm trying to find a time, t, when my A of t is equal to A0. So the objective is find t when A of t is equal to 0.1 A0. That's what I want to do. So let's plug it in. I get 0.1 times A0 is equal to A0. So I plugged in my A of t equal to that, the left-hand side. A0, e to the minus the natural log of 2 over the half-life of carbon. We are given that is 5,730 times t. So this is a governing equation that's going to allow me to find how old that artifact is. What I'd like you to do is, since you learned how to solve exponential equations, to solve that. Take that equation and solve that for t. And get an estimate for what t is. I'll go through it if you don't get the answer. If you can solve it, and I'll show you how to do it if you're not getting it. Got about 19,000 years, a little over 19,000 years. Okay, does anyone want to see how I got that number? How did I solve that equation? Okay, this is what I'm going to start with, this equation over here. 0.1, A0, e to the minus natural log of 2 over 5,730 times t. First step here is I will divide both sides by A0. Notice, it cancels out. So it's independent on the exact initial amount, just its relative percentage. I get 0.1 is equal to e to the minus the natural log of 2 over 5730 times t. I need to solve for t. How do I do that? I take the natural log of both sides. That will give me the natural log of 0.1. This cancels the exponential out and gives me minus the natural log of 2 over 5,730 times t. I can easily solve that for t by multiplying both sides by 5730 and dividing both sides by negative the natural log of 2. And I get t then is equal to minus 5,730 times the natural log of 0.1 all over the positive natural log of 2. There's the exact value. Now what do I need to do? Plug that into my calculator and get an approximation, because that's the exact value, but we'd like to see, take my natural log of 2, multiply that times 5,730, and divide that, the natural log of 0.1, excuse me, I'm off there, natural log of 0.1, okay. So 0.1, okay, then divide by the natural log of 2. Ln of 2. And I get 19,034 point whatever. So t is the t with the negative out front. I get 19,034.64798. So I'm going to say t is approximately equal to 19,000 years. So that's when that particular site was first inhabited by living creatures at that time. That's a good estimate. And that's how you do it. You just simply do that as shown there. Okay, let me just take a quick look, make sure. Okay, no questions. Okay, any questions on that? Now, this applies for the half-life of anything. You could look at the drugs in a body. If you know the half-life, I can follow the same exact procedure and find the time, how old that artifact is.
Professor, I think you can't see my hand raised. Can you just go over that last step right before you box it in? I didn't follow you.
Okay, let's do it in pieces over here. 0.1 is equal to minus the natural log of 2 over 5730 times t. Well, I could multiply both sides by 5730. Cancel, cancel. So I get 5,730 times the natural log of 0.1 is minus the natural log of 2 times t. I want to clear out this over here, minus the natural log of 2 on both sides, minus the natural log of 2, clears it out, and then I just pull the negative up top, and I have t, this is just equal to t on the right-hand side. T is equal to essentially that. Just solving a basic linear equation. And that's always how you can estimate the time. Now, if you turned out to be, 1/100th the amount, it would be much older. If that was 1% instead of 10%, then it would be 0.01, and it would scale this up rather dramatically. So that's all it is. That's how you deal with radioactive or carbon decay. But again, this is applicable to anything. It could be drugs in your body. Sometimes drugs decay in a matter of hours or days. That's why with drug testing, they can always test. They have a certain window until it gets to an insignificant amount that it falls beneath the level that they can't test for it. And they can estimate what that is. In forensic science, it's also used for, your body temperature goes down at an exponential decaying rate too. So they kind of, all these things kind of work this way too. And it's obviously based upon a lot of different things, like the environment that you're in and everything else. But exponential estimation is useful in a number of different areas. Okay, so this is exponential decay or decreasing. Well, it also goes the opposite direction. Let's take a look at a model to model exponential growth. Now, this could also be used to model the growth of the coronavirus, which they do in the models that they are currently using. Now, it will not grow indiscriminately. Eventually, because there's a finite population, it'll overtake the entire population. So it starts up like this. If you look at, for spread of disease, that's why we know how this works. That's why scientists are so concerned. It'll start out small and then quickly go up. But then you'll get to the point where most of the population is either, infected and they're either recovering or they died, and it'll slow down. So this is the exponential increase, and then it slows down eventually to a maximum. 100% is infected. Now this is called a sigmoid graph. So we're not going to go into these, but you can go beyond my basic increasing exponential and turn it around to decreasing. And you see that sort of happens as part of the exponential increase that has a fixed amount. For example, we're going to look at population growth as an example of an increasing exponential. Now, the governing equation for this, or the governing model, is the population as a function of time is equal to some initial population times by natural exponential times r, which is the rate of growth written as a decimal, percent rate of growth written as a decimal, times time. Now, even for population growth, if this was instead of the spread of disease, it was population growth, populations cannot grow forever. It's all depending upon the environment they're in. Like the Earth has a specific carrying capacity, how many humans it can actually carry with the present technology and the resources available. I think the last time I looked, it was about 28 billion. Now that'll change. It always goes up. And we're at, roughly around 8, just under 8 billion. So we're not at our carrying capacity. But if we were to grow unchecked, we could reach that carrying capacity. And this is kind of like the carrying capacity over here if you're dealing with exponential increasing. But we're going to not look at this phenomenon. We're just going to make it a little simple and just going to estimate, assuming that we are well away from that capacity for that to impact us. And this is the model that models population growth. So how might we use it? So here's an example of a problem. Let's say we have about, overestimate, say there are 340 million people in the US. Today. It's not quite that, I think it's a little bit lower than that. I'm just picking a general number. Now, if we were to grow at, well, pick a reasonable number. Sometimes people say, 5%. That doesn't sound too bad. 5% per year. How many people would there there be in, say, say 2050. I'll give you 30 years from now when, some of you will be starting to think about retiring and stuff like that, starting to think about it. Okay, so that's the question. Well, we can use this to model that and give an estimate for that. So what do we need to know? Well, there's certain parameters we need to know. We need to know what P0 is, and we need to know what R is. P0 is the initial population. So in that case, that's 340. And I'm not going to write all the zeros. I'll just use M, capital M for million. Mega is like million. The interest rate written as a decimal, well, that's 5%, is 0.05. That's 5%. Always write it as a decimal. If you don't, it's going to really increase at a phenomenal rate. Now we want to model my time t I need. At what value of t? At time t is equal to 0, that's today. If I put in e to the 0, I get 1, so I just get my initial population. So t equal to 0 is today. But I want to find t in the future. Well, that is equal to my 2050 minus today's date, 2020, which is 30 years. So I'm looking 30 years into the future, so that's the t I'm going to use. So now I looked at that, and I want to find the population in 30 years. Using this, so the population, P, after 30 years, is equal to 340 million times e to the 0.05, and this is where I'm putting my t is equal to 30 times 30. Well, let's put that into our calculators and see what we get, and our answer is going to be in terms of millions. So I'll take 340 times e to the 0.05 times 30. And in that case, I would have 1,000 and that's to approximately million, or approximately 1.5 billion. That would be a phenomenal amount. We are not growing at 5%. 5% doesn't sound like such a large rate, but it is. Now, when I say they're growing at 5% per year, that is just to be for those that often question this. This is the birth rate minus the death rate. It's the net growth. So this also automatically takes into those that are dying as well. I mean, obviously, if your death rate is higher than your birth rate, your population is decreasing. Not a state you want to be in. That's a catastrophic state. And that's when if some virus was to take over and wipe out the human race, that would be something catastrophic. Now, we do not grow at that rate. Typically, we've been growing at 1% and sometimes a little bit less. And in fact, in the United States, we're growing at less than we really need. If you're looking at people, if we didn't have any immigrants coming into this country, we'd be in trouble in probably about 20 to 25 years. We would not have enough young people to support the old people. There wouldn't be enough taxes, and we'd have to do something, because there'd be too many old people that couldn't support them. We need the immigrants. That's the same thing over in Europe. They need the immigrants too, because that's the only way they can get enough people to get jobs, to pay taxes, same the ones that are currently there. Because what happens in industrialized nations, as you get more and more technology, people have fewer and fewer children. So right now you have couples, we used to be in the old days after World War II, there were a lot of kids, everything was booming, everything grew. Now it's not the case, people get married, they may only have 1 or 2 children. They have 2 people creating 1. So what happens over time, your population goes down. You can't sustain that. How do we do it? We bring in immigrants. Bring them in and they can help sustain us. We really actually need them. Otherwise, we'd be in trouble. we'll never grow at 5%. If the world grew at 5%, we'd quickly get close to our carrying capacity. In 30 years, we'd be nearly at the carrying capacity of the Earth with the technology, even with the improvements in 30 years, that we'd be mass starvation and problems. But this is what they do. They estimate this. Now, this first model was put forward in the 1700s, 1798, by Malthus. He observed that, populations grow exponentially. And they've been always predicting, catastrophic things that never quite happen. You heard of the Malthusian principle? That's where it comes from. He was a cleric as well as a scientist. So he, he was religious person as well as a scientist, and he was putting out population growth way back when. Okay, so that's another use of our exponential function. So you might see something like this. That's how you can do it. You need these basic quantities, plug them in, and out you can pop the answer. Now you can also use this in biology to look at how many bacteria there are present and how bacteria grow. They grow exponentially. And the spread of a disease is also part of that. You get a few parameters. This weight is important. You need to determine that weight. Once you determine that weight, you can predict what's happening in the future, as long as you know the initial amount and everything else. So you'll see some other problems, not just populations of humans, but populations of other quantities as well. Okay, so that's an example of exponential, if you will, growth versus the other one, which was decay. Now notice here, this coefficient here is positive. That's why it increases. And it's an increasing exponential function. Goes in that direction, not decreasing. We should have learned that from when we examined our exponential functions. However, at the very end of the course, in chapter 10, we're going to review this all again and take you back to all the different functions and analyzing them as models, because that's really what you want to get to that stage. So when you get to the calculus, you can make statements about these models. Okay, so let's take a look at the last application, and that is scale applications. And that's logarithmic models. And that's how logarithms can be used to give us manageable scales. So we're now going to look at how to use logarithmic functions to model certain scales. And we're going to look at the Richter scale. And this is a model used to give us a nice manageable scale instead of throwing wild numbers at people, to give them simple numbers so they can estimate the magnitude of an earthquake. How big of an earthquake? How much shake is there on that ground? And this is all to find the magnitude of an earthquake. Now, since Richter, there have been many modifications of this, improvements and different sorts of scales, but this is the grandfather of all of them, so that's what we'll kind of look at that. And what Richter decided, okay, you say, let's A0, they use the seismometers, the things to measure the vibration of the earth. That little thing that, you've seen things that ticks up and down and does all these sort of things. It's called a, seismometer. And this is the seismograph. And if there are no earthquakes, you get an amplitude. It's kind of like a sine wave, if you will, an amplitude. So A0 is kind of like the background vibration of the earth. It's the amplitude of the normal, meaning no earthquakes, background vibration in the earth, Earth's surface. And let's A equal to the magnitude of the amplitude of how much vibration there is from an earthquake. So A is the amplitude of the Earth's vibration caused by an earthquake. And this is the model that we use. Let m equal to the magnitude. So m is the magnitude. And for that, we just kind of introduce that it's just equal to, we use the common logarithm. So it's the log of a over a0, where the log, that's the common logarithm. Remember that again. Is nothing more than the log in the base 10. So that's the connection. The log is the log in the base. It's defined to be that. And that's the same button if you look on your calculators. You have an log and an ln button. Those are commonly used, natural log and the common log. So this is the model we use for that. This is the model you use for a lot of different things as well. Okay, so let's take a look at a problem that you might see from this. So here we have an initial 5.7 magnitude earthquake occurred. Magnitude earthquake occurred. Followed by another earthquake with a magnitude of 8.9. Followed by another earthquake of magnitude 8.9 on this Richter scale. That's the assumption. The question we have is, how much larger in terms of the amplitude is the second relative to the first? So here's the real question. How much larger in amplitude is A, this capital A, is the second earthquake relative to the first? Not the Richter amount. The Richter magnitude amount is just, 3.2. But let's see the actual amplitude that's moving first. Okay, let's see how we analyze this to give us our sense using our logarithmic model there. So we're comparing these two earthquakes. So let's take a look at the two of them. Here's earthquake 1. And we have 5.7 is log of the amplitude A over A0. A0 is constant between the two of them. A0 doesn't change. A is the only thing that's changing. That's our basic baseline vibrations that are normally seen in the Earth. So I'd like to solve this for A. How can I do that? Well, I undo the logarithm by taking 10 to both powers, to both sides. So I get 10 to the 5.7 is equal to A over A0. Okay, well, let's take this 10 and raise it to that 5.7 power and see what we get. So 10 raised to the 5.7 power, I get, looks like 501,187 approximately is approximately equal to A over A0. I can do that calculation. Or the amplitude is about 500,000 times larger than the background amplitude. So there's the amplitude for earthquake 1, we'll call that. Okay, now let's take a look at the amplitude of earthquake 2. Relative to the background vibration of the Earth that occurs from normal, shifting of the plates and everything else within the earth and things happening. And little volcanoes causing all sorts of background noise, if you will. Well, now for the earthquake 2, I'm dealing with something that's magnitude 8.9 is equal to the log of A over A0. Now I want you to tell me what my amplitude for earthquake 2 is in terms of earthquake, in terms of the background A0. I want you to solve the same thing I did over here. Make sure you can do that. They get 794,328,000, roughly 235. I rounded to the last place, times the initial background vibration in the earth. Is everyone getting that? Anyone want to see how I did that? Just raising this 10 to that power, 10 to that power cancels, and then I just multiply both sides by A0. Okay. Now let's answer the question. What is the relative size difference? So what I want to take is my amplitude of the second one divided by the amplitude of the first. So that's my 794,328,235 A0 over 501,187 A0. What happens to A0? It cancels out. So when I look at a relative measurement, I don't care what the initial background vibration is in the earth. It cancels out. So I want to look at the relative size differences over here. This gives me approximately equal to 1,585 times as large. Get a lot of bang out of one, even, from 5.7 go 3.2. 3.2 increase on the Richter scale is a factor of almost 1,600 times the size of the previous earthquake. It's a large scale, scaled down to small numbers. So when you hear something increasing by, 1, 2, or 3, Richters in magnitude, it's a big increase. Now, one increase, because it's a logarithmic scale, so it's a funny scale. One increase is a fact. If you go up by 1, it's a factor of 10. If you go up by 2, it's a factor of 100. If you go up by 3, it's a factor of 1,000. If you go up by 4, it's a factor of 10,000. It always goes up by a power of 10 in each case. That's why just going up by 3.2 is nearly 1,600 times as large as the other one. It gives you some sense for the numbers don't sound bad. Oh, well, 5.7 to 8.9 doesn't sound so bad, but it actually is much worse than one could imagine. And that's how you do some problems like that. How you would work and use the logarithmic function to give you a scale that we interpret things on today. Now, most people, men and women on the street, they don't understand this. They have no idea. And it goes up by 3 or 4. If you went from an earthquake, very simple in direct calculation, if you had an earthquake that was, say, 4.0, and then one went up to 8.0, how big would that be? How much larger would this one be than the other one? 10 to the 4th power, or 10,000 times bigger. 10,000 times bigger. So that's a big phenomenon. Now, if it went to a 9.0, how much larger would it be? 100,000 times bigger. If it went from a 4 to a 10.0, that's 1 million times as large. Very big scale over here. And you know, if there's a certain amount of devastation, imagine the amplitude going 1 million times larger than that. It just kind of wipe everything out in many ways. And that's why we don't get too many, very rarely do you get something in the 9s. Luckily for us. Once you get to that max, otherwise it's like major destruction. But it gives you a newfounded appreciation for the logarithmic functions, because they take large quantities and scale them down to small quantities, like going from 1 up to 10. Usually you don't get anything over 10, because if you went up to 11, that would be 10 million times, and that would be just unbelievable.